In this lecture, we will introduce how to do wireless serial data transmission using an XBee Wi-Fi chip and the serial communication protocol that we talked about previously using the USART. So the XBee chips that we will be using in class look similar to the ones pictured here. Ours are a little bit different in that they have a stubby rubberized antenna built into the top of them. And these are fairly nice modules. They are relatively low cost and they allow us to send and receive data over a network. Now, some XBee chips like this are used for Zigbee mesh. We're going to be using ones that are designed to work with an existing Wi-Fi infrastructure, and we'll talk a little bit later in perhaps the next lecture about different wireless transmission protocols and what the differences are between Zigbee and Wi-Fi. But basically what you need to know about these chips is that they have a built-in antenna for some of them. In the case of the one like you see here on the right, it's got an extra coaxial port for you to be able to screw in an antenna, generally for longer range transmission, and they do rely on serial communication to send and receive data. The pin diagram is going to be in a following slide, but what you need to know is that there are several general purpose input-output ports on the XBee, and they also have the capability of doing some analog to digital conversion and sending that information across the wireless network. And they can use several different serial data formats, and that is something that can be configured on board the XBee chip. So here's the basic pinout. It is a 20-pin device. VCC needs to be supplied a power. In this case, it's going to be 3.3 volts. And then you've got pin 2 and 3 where your data out is being sent out. You're going to be receiving on that. And then your DN is where your data is coming in. And so that is what we're going to be using for our data sending and receiving. And then we're not going to use several of the other pins in here. A lot of this is digital input output or used for other serial transmission protocols. We will need to give a ground reference here on pin 9. Obviously you want the same common ground as what you have with your PIC microcontroller. And then over here on pin 15, this will help us to do a little bit of error checking just to make sure that our network is receiving appropriate data. We are going to be using this associate pin, which will blink an LED for us just to showcase that we are talking to the network appropriately. So the XBee chips come without much configuration on them, and we can use a software called XCTU to configure them. And there's several different things that we'll need to program in. One is what SSID they will be associated with, that is the network that they are going to connect to. And then we will also need to put in, if that network has security enabled, what the password is to access that network. We're going to have to program in the baud rate that we're going to be using. We're going to use 9600 baud for our projects in this class. And then you can enable certain security settings, so you can choose what security protocols you want to use, whether that's WEP or WPA. And then you can also put in the address for this chip to send to on the network. And so you can choose to send to one specific address, so that is basically you're just sending data back and forth one-to-one, or you can do a bit of a more global broadcast, and I'll showcase that in the class. That's what we're going to be doing. Is my transmitter will broadcast to all of your XBee chips, and then you guys will receive my signal over the network. You can program in what the transmission protocol is, whether you're using TCP/IP or USART or various other protocols, and then you can also determine how the IP address is configured. So the IP address is basically like your mailing address on the internet, and it is typically dynamically created using DHCP, which basically goes out and looks on the network And when your device powers up or just starts, before it starts transmitting, it will generally just pull whatever IP address is the next one available and assign that to you. Alternately, you can have a static IP address, which is useful for some applications, where basically you maintain the same IP address all the time. This is very useful for things like websites that you want to always access in the same place, or anything else where you want to always know what the address is to send your data to without having to go through a dynamic allocation process. And so this configuration is saved on the chips. It's saved into a EEPROM, and then when we put it in range of the network it's configured to do and properly power it up, it will be ready to send or receive some data. So the connections that we'll need, we're going to have VCC, and that's going to require 3.3 volts, which we can't get natively out of our trainer kit, so we're going to have to use a 3.3 volt voltage regulator. And then pin 2 is where we're going to connect our RX. That's the data coming out of the Xbee, which will be sent to our receiver on board the PIC. So we're going to connect that to RX, and then if we're transmitting, the data that is going into the Xbee is going to be coming from our TX on our PIC. And then pin 10 is going to be our ground, and 15 is going to be solid when it starts up and is powered on. And then once it begins talking to the network, after about 10 or 12 seconds, it will start blinking. So there is a little bit of a slow power up on these chips. So here's the basic schematic of what we're going to need here. Pin 1 is going to be the output from this voltage regulator circuit. So here's how the regulator works. You've got an input voltage, that's going to be your 5 volts. You've got an output voltage, that's going to be the 3.3 volts, and you've got a ground reference. And we will also need to put in a capacitor. These particular voltage regulators need to work with the capacitor in order to make sure we have the proper amount of current going into the Xbee at the input voltage pin. And so we'll also, on the associated, we're going to put a resistor going through an LED to ground, and that way we'll be able to monitor that particular pin. We're going to be using the USART just as was described in the previous lecture, and so we'll use the same bits and registers that we talked about last time. And so just a refresher, the baud rate is set by this formula here. So if you're clearing BRGH, it's a divide by 64 in this formula. And remember, FOSC for the trainer kits that we are using is 4 million. We have a 4 megahertz oscillator. And SPBRG is determined based on what baud rate we want to use. Similarly, if BRGH is equal to 1, same formula, except this becomes a 16 instead of a 64. And for 9800 baud, you can either compute that or look it up in a table in the data sheet. We're going to set BRGH to 1, and then SPBRG we're going to make equal to 25. And so the baud rate is going to be set according to this formula. If you put in this 25, then what you're going to get is a baud rate of about 9615, which is a little bit higher than what we wanted to, but not too much. So just to review our transmit status and control registers, this is in TXSTA, which happens to be in bank 1. We're going to be using the asynchronous mode. So that means we don't care about what's in bit 7 because that's used in a different mode. Bit 6 is your TX9. You're going to want to make sure that's 0. That, if it were set to a 1, would be enabling 9-bit data transmission. We only want 8, so we're going to clear that. TXEN you will want to enable if you are going to be transmitting. For your project and in lab this week, you're not going to be transmitting. I will make the transmitter and you will just be a receiver. Then in bit 4, that is your sync bit. So that is whether you're in synchronous or asynchronous mode. We're going to be in asynchronous, so set that bit to a 0. And then send B allows you to send a break. And we're not going to be using that particular bit. BRGH, we're going to put to 1 for high speed mode, and that's what we're going to do. And then TRMT tells you about the status of the shift register, whether it is empty or full as the data is getting transmitted. And then the last bit here, TX9D, is just used for the 9th bit. If you are going to be sending 9-bit data, since we're not going to be using that bit at all. And then RCSTA helps to configure the receiver for the most part. SPEN is a bit you will want to set to enable the serial port, whether that is as a receiver or a transmitter. And so we are going to enable RC7, which will be RX, as an input, and then RC6 as TX, which will be an output there. And then RX9 is a bit to determine whether you are going to be receiving 9-bit data. Again, we're not, so you can just set that equal to 0. And then SREN, bit 5, is a don't care in asynchronous mode, which is what we're going to be in. Bit 4 allows continuous receiving of data. And so as you send data across, it will automatically pick it up whenever data is available. You don't have to worry about bit 3, that's only for 9-bit mode. Bits 1 and 2 are useful for some error checking. And then the last bit there, RX9D, is the received 9th bit. But since we're not dealing in 9-bit mode, you can ignore that pin, or that bit. So the general transceiver setup, you've got to set up your baud rate using the formula that we already talked about. You have to enable the asynchronous mode by just setting sync equal to 0. Then you want to enable your serial ports, so say SPEN equal 1. And then you want to set up for the 8-bit mode. So both our TX9 and RX9 are going to go to 0 because we are not transmitting or receiving 9-bit data. And then if you are programming the transmitter, make sure TX equal N is equal to 1. If you're programming the receiver, make sure CREN is equal to 1. So that's for transmitting is basically enabling the output, and for receiving is enabling continuous receipt until you change your settings otherwise. So to start the transmission, what you basically need to do after you've already properly configured the baud register is write an 8-bit value to TXREG. And so that is your transmit register. You just put whatever value you want to send across in there, and then it goes into the shift register and gets sent out one at a time. On your receiver side, you can simply poll RCIF using the code that you see here, and when it goes high, the data happens to be ready. And so in this particular case, we're going to wait until this while statement is not true, and then we will be ready to process that particular data. And so once that flag is properly indicating that the data is ready, then you can receive the data from RCReg. It is important when you are working with sending and receiving data, if you want to configure a device as a transceiver and have it talk to another transceiver, it is important that you coordinate so you know how many packets of data will be coming across before you send data back. Timing is very critical on things like this, so you want to make sure you know when you're expecting data, what type of data, and you want a handshaking process where you either send over a special character that indicates it's now the other system's turn to send back, or some kind of a timing process in there to make sure after a certain time only other devices have opportunity to send across the network.